In this video, we are going to talk about another energy storage element called the inductor. And let's first look at what does an inductor physically look like. Imagine you have a core material and you have a wire wound around it. This is called a solenoid. And I'm sending a current through the wire. And as a result, there's going to be a magnetic field being created. So that's the magnetic field B here. Okay, this is something we know from physics. There's something else we know from physics, which is, well, if I have a solenoid, and imagine I have a magnet that I'm moving towards or away from my solenoid, what Faraday observed is that this actually created a voltage difference between the two terminals. And Lenz's law says that the induced voltage is actually in the direction such that it opposes the change in magnetic field. Now, what does this mean for our system here? So, imagine that I'm changing the current here. If I'm changing the current, because my magnetic field is proportional to my current, this means that my magnetic field is changing. And what Faraday's law says is there's a change in magnetic field, there's going to be an induced voltage. And Lenz's law says that the voltage has a sign such that it opposes the change in magnetic field. So in this case, the voltage is going to appear like so, because this voltage is actually opposing this increasing current. This voltage makes it harder for that current to flow, right? It's trying to push it back. And so this is how an inductor behaves physically. And this is the symbol we're using for an inductor, for an ideal inductor. So we're again using the passive sign convention. And the induced voltage is proportional to the change in current because of Faraday's law. And the sign of the voltage here is because of Lenz's law. And if I look at the proportionality factor, I call this L the inductance of my inductor. Again, this L depends on the physical parameter of my inductor. It depends on the material property called the permeability, and also on the physical dimensions. So it depends on the cross-section of the solenoid, the length, and then N is the number of windings. The units of inductance are the henries, and typical values are the few henries to microhenries. Okay, so I have my relationship between voltage and current for my inductor. And just like for the capacitor, it is the time difference. In this case, it is the change in time of the current that's going to determine my voltage. So for the capacitor, it was the change in voltage that determined the current. Here it is the other way around. And I can again write this in integral form. And the same thing, I in principle need to know what's happening all the way to the beginning of time. But I can split up this integral in two parts. So I can say, well, if I already know my current at some point in time, I can just look at the time evolution from that point forward. Okay, so this is an inductor. And an inductor is a linear element. Just like a capacitor, just like a resistor, an inductor is a linear element. So anything we know about linear systems still holds when we have inductors. Now, inductors, they seem a little bit counterintuitive to work with. So let's actually look at the hydraulic analogy. A resistor, remember, was just a pipe. An inductor you can look at as a water wheel. So suppose the water wheel is standing still. I need to exert some force to push the water through here to get this thing up and running, to get it spinning, right? So the actual amount of force relates to the change in current. Initially, nothing can flow because everything is blocked, but slowly the current will increase as I keep pushing water through it, right? And so how much I push determines how fast I'm spinning this wheel up, so how much the change in how much of a change in current is going to occur. Now, once it's up and running, once it's spinning, and I'm not changing the current anymore, how much water is flowing through this, I don't need to exert any force. So if di dt is 0, v is 0. So once this is spinning at a constant speed, I don't need any pressure difference anymore. Right? So this is the analogy of an inductor. For an inductor, to have it change the current, you need to apply a voltage. But once you keep the current constant, there is no more voltage difference over the inductor. You may wonder, okay, so this is the inductor. What's the analogy for a capacitor? This is what the hydraulic analogy looks like for a capacitor. I find it less useful. It's basically a membrane that blocks the water, but it pushes water. If you push it in one direction, the current flowing in this direction is pushing the membrane out, which then pushes more current in the other direction. So current actually doesn't jump across the membrane, but these two currents on both sides are actually equal. And the membrane actually stops expanding because it creates a force pushing against the water. And so eventually there is not going to be any change in voltage anymore. So basically the current will actually stop once the force you push in this direction with the water and the membrane cancel each other out. Again, this is a little bit of a less intuitive analogy. And so it's not important if this doesn't totally make sense. Okay, so let's actually get back to our inductor now. And we can also look at the power consumption of my inductor. It is, again, V times I because I'm using the passive sign convention. And let's look again at how much energy is stored in my inductor. So it's the integral of all the power that was received. Again, plug in the equations. And assuming that there was no current flowing at the beginning of time, I get an expression of the energy stored in an inductor, which depends on the current. So the way to think about this is when there's a current flowing through an inductor, there's a magnetic field. And this magnetic field actually stores energy. So by putting current through an inductor, you're creating a magnetic field, and so you're actually storing energy in an inductor. And again, let's look at how an inductor behaves when I change the voltages or currents. So in this case, I have a current through an inductor, and I'm changing it according to this graph over here. So between time 0 and 1, well, if I know the current, I can calculate the voltage. It's just the derivative. So this is what the voltage does. Then between time 1 and 2, the current is constant. So again, looking at that same equation, when there's no change in current, the voltage is equal to 0. So that also corresponds to my analogy with my water wheel, right? If I'm not changing the flow of water, it's just spinning at a constant rate, I don't need to push anymore. Same for an inductor. If I don't change the current in my inductor, I do not need any voltage over it. There's actually going to be 0 voltage over my inductor. So now what happens when I disconnect my inductor? So at time 2, I disconnect it. What does that mean is that the current drops to 0, right? Because if I disconnect it, it's basically just an open circuit. There's just an inductor. There cannot be any current, so the current is forced to 0. Well, what happens is when the current has this sudden jump, at this point, I'm going to have an infinite voltage over my inductor. And again, this is not physically possible. So for an inductor, what's true is that the current through an inductor cannot change instantaneously because of this. So that's a very important property of an inductor. When you have a current going through an inductor, you cannot suddenly disconnect it. You're going to have problems because a really, really large voltage is going to appear. Again, this is the model of an ideal inductor. So what would actually happen in practice, you wonder, if I take an inductor and I just disconnect it? Well, you would indeed have a very large voltage between the two terminals, which would ionize the air, and basically you would have a spark. And this is not covered in these ideal models. But whenever an inductor is in the real circuit, when there are resistors and other elements, this can actually not happen. You can never have an infinite voltage, and so for an inductor, it's always true that the current cannot change instantaneously. Okay, so now let's look at what happens if I apply a voltage to an inductor. Well, I can calculate the current with this equation. So it's just the integral. So this is what the current is going to do. And then between time 1 and 2, the voltage is negative, and my current is going to go like this. Now, let's look a little bit closer at these different time intervals. Between time 0 and 1, my voltage is positive, my current is positive, and I'm using the passive sign convention here. So here, my inductor is receiving power. I'm starting to store energy in my inductor. Then at this point in time, between here and here, my voltage is negative, my current is positive. I am actually delivering power. So between those two times, my inductor is actually giving power back to my system. So it is supplying power. Between these two times, 1.5 and 2, my voltage is negative and my current is negative, so the product is again positive. My inductor is receiving power again. So my inductor can basically first take power, then give it back to the system, then receive more power. A capacitor can do the same thing. That's why these are called storage element, energy storage element. You can put energy on there and then you can take it away. Okay, so let's summarize what you know about inductors. The current through an inductor cannot change instantaneously. That means that the current waveform has to be continuous. Number 2, an inductor stores energy, and it does that in the magnetic field. So when the current isn't changing, or when an inductor doesn't have a voltage over it, it will keep the current constant. So if there's no voltage over an inductor, the current will be constant. Follows directly from the equation. And then finally, an inductor, just like a capacitor, has memory. It depends on the past. So this is basically what inductors are and how they behave.